Jupiter is our solar system's largest planet. It's more than twice the mass of all the other planets combined. Its swirling atmosphere moves in bands at different latitudes, and its great red spot is thought to be a perpetual storm. Recently, images from a new probe that has flown above Jupiter's poles reveal a completely different planet. The ancient Romans knew Jupiter as the celestial representation of the king of the gods. In 1610, Galileo, using his newly improved telescope, saw Jupiter's moons and could see they orbited the planet, evidence that not everything revolved around the Earth as the Church had declared. Though better telescopes improved our view of Jupiter, it was not until 1964 that Gary Flandreau, a graduate student working part-time at NASA's JPL, understood there was a way to get a clearer look at Jupiter. By plotting the positions of the outer planets, he realized that a rare alignment would enable a spacecraft launched in 1977 to visit Jupiter, Saturn, Uranus, and Neptune. NASA jumped at the opportunity and began work on twin craft for what was then known as the Planetary Grand Tour. To limit any surprises, two basic spacecraft, known as Pioneer 10 and 11, were quickly built. They would go ahead of the Grand Tour missions to send back information about the environment. Pioneer 10 was launched toward Jupiter in March 1972. It was the first spacecraft to cross the asteroid belt that lay between Mars and Jupiter, and because it was the first probe on a trajectory that would take it out of the solar system, it carried a plaque identifying its origin. By December 1973, Pioneer 10 was sending back pictures of Jupiter clearer than anything that had been seen before. Approaching Jupiter, it encountered levels of ion radiation 10,000 times more intense than the radiation belts surrounding Earth. As the probe skimmed past the giant planet, it gained speed. Leaving Earth, Pioneer 10 was moving at 51,000 kilometers per hour. Departing Jupiter, it had more than doubled its speed. This gravitational slingshot effect made the Grand Tour possible. The Grand Tour craft, recently renamed Voyager 1 and 2, were due to be transferred to Cape Canaveral for launch integration when news of Jupiter's extreme radiation environment came through. The electron radiation at Jupiter had generated false commands within Pioneer 10. With the far more sophisticated Voyagers, this presented problems. Local supermarkets were stripped of their stocks of kitchen-grade aluminium foil, which was then used to shield critical cables. Without this last-minute alteration, electrical pressures of up to 40,000 volts would have been induced in the Voyager's subsystems as the craft passed Jupiter. Voyager 2 was launched in August 1977. Its trajectory meant that it could visit Jupiter, Saturn, Uranus, and Neptune.
To extend man's senses farther into the solar system than
Voyager 1 left 16 days later. Its different, faster trajectory only allowed flybys of Jupiter and Saturn and various large moons. At the time, the Voyager spacecraft were the most sophisticated probes to be launched. Because they were to operate at huge distances from the Sun, solar panels could not be used as a power source. They were equipped with radioisotope thermoelectric generators which use the heat from the decay of plutonium-238 to generate power. As Voyager 1 approached Jupiter in January 1979, it began sending image sequences that showed a complex and dynamic planet. The planet's giant red spot was revealed as a vast rotating storm. In 1665, Giovanni Cassini described a permanent spot on Jupiter which was regularly observed into the 1700s. It was not until the late 1800s that Jupiter's spot was described as red, and it's uncertain whether the historic observations of Jupiter's spot refer to the same feature or a phenomenon that regularly manifests in Jupiter's atmosphere. Voyager 1 made its closest approach early in March 1979. As the probe neared Jupiter, the activity at NASA's Jet Propulsion Laboratory became intense. This was the nature of the Voyager's flyby missions. There were long, quiet cruise phases between the planets, followed by brief periods when the flow of information from the craft overwhelmed researchers. One of the biggest contributions made by the Voyagers was the transformation in our understanding of the Galilean moons. Previously just dots of light, Jupiter's 4 largest moons were each distinct and completely different. The first surprise was the inner moon Io. It's a sulfurous yellow in appearance, and one particular long-duration exposure revealed an odd plume. Rather than being a cold, dead world, the gravitational squeezing Io receives from its giant neighbor heats the moon's interior. The plume was a volcanic eruption, ejecting material hundreds of kilometers above the surface. In July 1979, 3 months after Voyager 1 had moved beyond Jupiter, Voyager 2 made its closest approach. It was able to examine different moons more closely than its twin. Europa was the next surprise. It is highly reflective and has the smoothest surface of any body in the solar system. Further observation revealed pressure ridges reminiscent of polar ice flows on Earth. Europa is a frozen world, with a vast ocean beneath a thick crust of ice. Like Io, it is heated from within by tidal flexing. As Voyager 2 continued toward Saturn, planetary researchers were left with large amounts of raw data about Jupiter still to be processed. The Voyager missions left us with a basic view of the Jovian system, but they had raised more questions than they were able to answer. It would be more than 10 years before Jupiter received another visitor from Earth.
Ignition and liftoff of Discovery and the Ulysses spacecraft bound for the polar regions of the Sun.
In October 1990, the Space Shuttle Discovery lifted the European Ulysses spacecraft to low Earth orbit. From there, it was boosted on a mission to observe the Sun, but first, it would pass Jupiter. All the planets orbit the Sun in the same direction, in roughly the same plane. This is called the ecliptic, and it developed from the spinning disk of dust and gas that formed our solar system. The designers of the Ulysses spacecraft wanted to see the Sun from an orbit above its poles. Jupiter's extreme gravitation was used to bend the probe's flight path out of the ecliptic so it could make north-south orbits of the Sun. Ulysses was not the only probe to take advantage of Jupiter's gravity. Both the Cassini probe to Saturn, launched in 1997, and the New Horizons probe to Pluto, launched in 2006, were able to reduce their flight times by years with Jupiter flybys. These probes were able to make meaningful observations while passing the giant planet. In the clean rooms of the Jet Propulsion Laboratory, a new probe was taking shape. Galileo would be the first spacecraft to go into orbit around Jupiter. Its 4.8-meter antenna was folded like an umbrella, only to be deployed when safely on the way to Jupiter. Originally scheduled to launch in 1986, it sat in storage for years after the Space Shuttle Challenger exploded.
10, 9,
It launched aboard Space Shuttle Atlantis in October 1989.
4, 3, 2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
New rules governing shuttle launches meant a change in the booster to push Galileo out of Earth orbit. The less powerful solid fuel upper stage, now stipulated, sent Galileo toward Venus for a gravity assist. The new flight path meant Galileo was traveling to a hotter part of the solar system. It was decided to keep the heat-sensitive antenna furled until after the spacecraft looped back past Earth. Galileo made 2 close passes of Earth, each time gaining more speed. Its first pass was in December 1990, more than a year after its launch. A further year on, when it passed Earth again, the high-gain antenna was only partially open. After months of trying different techniques to deploy the antenna, mission engineers concluded that long periods in storage had caused lubricant at the tips of the antenna's ribs to dissipate. Researchers would rely on Galileo's smaller antenna with data delivered at slower rates. During the cruise to Jupiter, Galileo encountered several asteroids. This is Ida, the first asteroid we've learnt of with its own moon, Dactyl. In July 1995, while it was still 6 months away from its closest encounter with Jupiter, Galileo ejected a small probe designed to enter the atmosphere and sample its chemical composition. The probe lasted for an hour in Jupiter's atmosphere. The data was relayed to Galileo and recorded for subsequent transmission back to Earth. Its analysis revealed hardly any water vapor, which was unexpected, and other elements, particularly helium, were detected at far lower levels than predicted. The probe experienced areas of extreme heat and cold, suggesting heat is being released from the planet's interior. Slightly more than an hour after transmission from the probe ceased, Galileo began its orbit insertion burn. Its engine had to operate for 49 minutes to put it into a highly elliptical equatorial orbit. But this orbit would be altered with another burn at its high point. Mission designers were acutely aware of the high radiation environment, and the second burn would lift Galileo above the extreme radiation at its closest approach. Galileo's initial orbit eventually delivered a close approach to Ganymede, Jupiter's largest moon. During this orbit, engineers were trying to understand damage to the spacecraft's vital tape recorder. Without its high-gain antenna, the recorder was essential for slow replay of data recorded during the brief, close encounters. It had been stuck in rewind for 15 hours, and tape had been degraded. Light-emitting diodes, key elements in the recorder's control system, had acquired radiation defects. The second orbit also passed Ganymede. Galileo discovered it's the only moon in the solar system with a significant magnetic field. It also has an ocean sandwiched between 2 layers of ice. Galileo's orbits would be slightly varied so that it could make close approaches to different Jovian moons. But the equatorial orbits needed to reach the moons also took the craft through hotspots in Jupiter's radiation belts. With the observations made by the Voyagers, the moon Europa was of particular interest to the Galileo team. Data from several instruments agreed that a salty ocean exists beneath Europa's surface ice. Later examination of the Galileo datasets revealed plasma wave and magnetic field information, showing that plumes of water vapor were erupting from cracks in the surface. Europa has more water than Earth, which makes it a possible home to life. Io was already known to have volcanic activity, but Galileo saw tides in the Moon's solid surface of more than 100 meters. The temperatures generated by this gravitational distortion of Io make its numerous volcanoes hotter than anything found on Earth. During its 8 years at Jupiter, Galileo completed 35 orbits, filling out our limited picture of the Jovian system. This was never an easy mission. Galileo was a robust spacecraft, but the radiation environment stressed all the subsystems, and engineers were constantly having to find workarounds for the frequent breakdowns Galileo suffered. Instruments showed increased noise when near Jupiter, and current leakages caused by radiation led to several resets of the onboard computer, with crucial loss of data. Software changes enabled the computer to recognize these resets and to recover by itself. Information learned would lead to changes in the way the next Jupiter spacecraft was designed.
Discover the past with exclusive history documentaries and ad-free podcasts presented by world-renowned historians, all from History Hit. Watch them on your smart TV or on the go with your mobile device. Download the app now to explore everything, from the wonders of ancient Pompeii and the mystery of the princes in the tower to the life of Anne Boleyn and D-Day. Sign up via the link in the description.
5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter.
In August 2011, Juno began a journey to Jupiter that would last almost 5 years. Its mission parameters would be very different to Galileo's. It would ignore the moons and focus exclusively on Jupiter.
Chamber pressures have plateaued.
Spacecraft design saw crucial electronics shielded within a thick titanium vault, and rather than a plutonium power source, Juno would rely on solar panels. The Sun's intensity at Jupiter is roughly 5% of what it is at Earth, so the panels are huge. A shortage in stocks of plutonium-238 led to the change in power sources. Juno followed a looping orbit that took it beyond Mars before swooping back to Earth for a gravitational boost that added 14,000 kilometers per hour to its velocity, sending it on to Jupiter. Juno approached Jupiter on a path that took it above the planet's north pole. It was destined for a north-south orbit. This would see it pass beneath the severest sections of the planet's radiation belts that extend out from Jupiter's equator. 4 days before its closest approach, Mission Control sent a command that initiated the craft's autopilot. On July the 4th, 2016, Juno began an engine burn that would insert it into a 53-day orbit. 48 minutes later, Mission Control at JPL received tones verifying that Juno had started its deceleration maneuver. It was a tense 35-minute wait from the system's engineers before confirmation came through that Juno had performed exactly as intended. For the Juno scientists and engineers, it was a relief that things were going to plan.
Roger the move, Juno.
Juno is equipped with a suite of instruments capable of penetrating Jupiter's thick cloud. The polar orbit allows Juno to compile a three-dimensional map of the upper atmosphere, building a picture of the entire planet as it rotates. The images of Jupiter from this new perspective appeared to come from a different planet. Researchers were stunned. It was planned that Juno would only make 2 53-day orbits and then change to a series of 14-day orbits that would speed up the sampling rate. The spacecraft's main engine is fueled by hydrazine and nitrogen tetroxide, which ignite spontaneously when mixed. The propellant and oxidizer are forced out by a bladder of expanding helium. As Juno was finishing its second orbit, the helium valves were not responding correctly, so it was decided to maintain the original orbit. A mission extension has been granted to allow for the longer orbits Juno continues to follow. Within a day of the helium valve problem, Juno went into safe mode. All instruments went offline and data was lost. It appeared to be similar to the difficulties experienced by Galileo, but engineers traced the issue to a data transfer problem from one specific instrument, and the spacecraft remains healthy. Jupiter's axis is tilted at only 3 degrees, making even an oblique view of the poles near impossible until Juno arrived. When viewed in the infrared, researchers saw a complex arrangement of storms at both the poles. At the North Pole, a central vortex is surrounded by 8 anticyclones. At the South Pole, 5 anticyclones surround the central storm. Scientists do not understand why the storms, all rotating in the same direction, do not obliterate each other. On its 7th close pass of Jupiter, Juno flew directly over the giant red spot. Its microwave radiometer was able to map the heat distributions at varying levels down to 350 kilometers. The red spot is a giant storm, and Juno was able to see much higher temperatures at the deepest levels they could penetrate. With no geographic features, as on Earth, there is nothing on Jupiter against which storms can dissipate. The Great Red Spot remains firmly 22 degrees below the equator, yet it appears to have drifted around the planet at least 10 times since reliable observations began. Jupiter's magnetosphere is huge. It traps charged particles in bands stretching out to vast distances. This gives sensitive electronics on orbiting spacecraft like Juno big problems. It was assumed that Jupiter's magnetosphere was generated, like Earth's, by dynamo action, the convective movement of an electrically conductive fluid deep within. So far, results from Juno suggest that this is not the case. The lumpy nature of Jupiter's magnetic field points to an atmospheric source. The giant auroras at the poles also seem to come from a different mechanism than here on Earth. By focusing on the composition of the gas giant, researchers are hoping to gather clues about conditions at the formation of the solar system. While the Earth has been continuously changed by tectonic forces, it is thought that Jupiter remains very similar in composition to the cloud of gas and dust from which the solar system was formed. At the end of its mission, Juno will be sent on a collision course with Jupiter to avoid any possible contamination of the delicate moons. The next mission to the Jovian system will focus on Europa, as the most likely place after Earth to harbour some form of life. Known as Europa Clipper, it's scheduled to launch in 2022. Like Juno, it will be solar-powered, and its elliptical orbit of Jupiter will see it fly over Europa every 2 weeks. Early concepts for the mission called for the inclusion of a lander, but this idea was soon rejected as premature because more needs to be learned about the surface of the icy moon. Though Europa's ice crust is thought to be at least 19 kilometers thick, accurate measurements need to be made. If thin areas can be found, then future missions may be able to access the ocean that lies beneath. Concepts for under-ice explorers are in development, and we can expect other missions to focus on other moons. As the largest planet, Jupiter's influence on the rest of the solar system is profound. It has more than twice the mass of every other planet combined. All other planets' orbits are affected by Jupiter's gravitation. There is still much to learn about Jupiter. For a human to work in space, he or she must have a spacesuit. It protects the astronaut from the vacuum beyond the atmosphere, supplying oxygen as well as insulation from the extremes of heat and cold. The spacesuit has to have means of communication with the outside world, and it must enable freedom of movement. The modern spacesuit is the result of a long and complex evolution. Long before humans had traveled to space, aviators wanted to fly at heights that could not support life. In 1932, Auguste Piccard flew above 16,000 meters in a helium-filled balloon. To stay alive, Piccard ascended in an aluminium pressure vessel fed with compressed air. Spanish aviator Emilio Herreras came up with a different solution. His stratospheric suit never flew. It was an idea ahead of its time. In the United States, aviator Wiley Post had supercharged his plane, the Winnie Mae. It could fly at 15,000 meters, where the jet streams blow. Post knew he could save fuel and fly faster at that height. So with the help of tire maker B.F. Goodrich, he devised the first serviceable pressure suit. At this time, even military aircraft were flying at much lower altitudes, where the use of a simple oxygen mask was enough to ensure pilot efficiency. However, as jet power was introduced, operational ceilings lifted. At high altitudes, low ambient air pressure meant the oxygen mask would lift off the face when oxygen was fed to the pilot at pressures high enough to sustain life. When bombers like the B-36 began long-duration missions at high altitudes, they adopted pressurized crew compartments. Yet the pressure suit, with a fully enclosed helmet, was necessary as sudden cabin depressurization could be lethal. In the 1950s, partial pressure suits became common. They had inflatable capstans that stopped blood draining to the legs under heavy G-forces, avoiding blackouts. Air crews hated them, but figures showed they functioned more effectively when wearing them. In 1955, a unique American spy plane made its first flight. The following year, the U-2 began reconnaissance missions over the Soviet Union. Flying at 21,000 meters, it was beyond the range of Soviet radar, and neither jet fighters nor missiles could reach it. Pilots flying the U-2 wore a new partial pressure suit, the MC-3. Rather than save a pilot's life in case of sudden depressurization, this suit was designed to be under pressure throughout the mission. Without it, the pilot's blood would boil. As missile technology developed, it appeared that human beings would be dispensed with as a weak link, not able to cope with conditions imposed by the technology. But the US Air Force had different ideas. They felt that a pilot could make better decisions than a guidance system, and they began a research program using hypersonic aircraft to learn about the problems associated with ultra-high speed, ultra-high altitude operations. The culmination of this program was represented by the X-15, a rocket-powered aircraft that could fly to the edge of the atmosphere. Because of its limited fuel load, the X-15 was launched from beneath a B-52 bomber at an altitude of 15,000 meters. The cabin of the X-15 was pressurized with nitrogen to reduce the risk of fire. For the pilot, a new full-pressure flight suit, known as the XMC-2, was developed. It too was pressurized with nitrogen. A neck dam excluded the nitrogen from the helmet, which was fed with oxygen for life support. This suit was the predecessor of NASA's most important spacesuits. The X-15 set the speed record for a powered aircraft at well above 7,000 kilometers per hour, and the altitude record at just over 107,000 meters. The first real spacesuit was worn by Russian cosmonaut Yuri Gagarin. In 1961, aboard Vostok 1, he became the first man to orbit the Earth. His suit, the SK-1, was to protect against capsule depressurization and to sustain him during ejection from his craft. The Vostok cosmonauts had to parachute to the ground because their capsules landed too heavily. Since 1959, the newly formed US space agency, NASA, had been working towards launching an American into space. 7 test pilots had been selected as the Mercury program's first group of astronauts. The first attempt would be a short hop. As the only booster available at the time, the Redstone lacked the power to reach orbit. An important part of the preparation involved the development of a spacesuit. As a starting point, NASA looked at the XMC-2 used for X-15 flights and the Navy's aviation pressure suit, the Mark IV. Both were full pressure suits. NASA decided that the Mark IV suit, worn here by Alan Shepard, was lighter and could be more easily modified for spaceflight. The boot leather and the suit's grey outer covering would be replaced by aluminized nylon for greater thermal control, and the helmet's rubber diaphragm surrounding the face was eliminated, with oxygen now entering via a hose at the waist to help cool the suit. For all 6 manned Mercury missions, the Mark IV suit performed well, but the demands placed upon it were modest. Like most pressure suits at the time, it served as a backup in the event of cabin pressure failure. Because this never happened on the Mercury flights, this suit was only ever pressurized at launch. In the early 1960s, the Soviet Union's space program was achieving an impressive list of firsts. For the United States, this was a source of national embarrassment. In 1961, the new president, John Kennedy, had boldly proclaimed that America should land a man on the moon before the end of the decade, and NASA was flooded with funds. This was the beginning of the space race.
I don't think we ought to waste any money, but I think we ought to do the job. And this will be done in the decade of the 60s.
The Mercury program was terminated early, in favor of a more complex series of missions with the aim of solving problems associated with sending a man to the moon. The Gemini program made use of a new 2-man capsule boosted to orbit atop a modified nuclear missile. Gemini required a new suit with new capabilities. NASA now understood future missions would have to last much longer. Suits would have to be more comfortable, and astronauts would have to leave their spacecraft in the vacuum of space. Gemini controllers were planning the first spacewalk. In the less open Soviet Union, they were also preparing for a spacewalk. Cosmonaut Alexei Leonov was practicing with an inflatable canvas airlock in temporary weightlessness in an aircraft in a parabolic flight path. He was wearing a new spacesuit, the Berkut, designed to function outside his Voskhod spacecraft. The airlock was needed because the new Voskhod still did not have solid-state electronics. Its thermionic valves needed air cooling so the capsule could not be evacuated. In March 1965, Alexei Leonov left the airlock on Voskhod 2 to float freely in space. It was another first for the Soviet Union. Soon, his Berkut spacesuit began ballooning to such an extent that Leonov could not reach his camera's shutter release, positioned on his leg. It was not until after the fall of the Soviet Union that the full story became known. The Berkut spacesuit had expanded so much that Leonov could not get back inside. Only by venting his spacesuit could the cosmonaut regain entry to the Voskhod capsule. Back at NASA, they heard that Leonov's spacewalk had been a resounding success, but they felt the Gemini program was catching up. In June 1965, astronauts Jim McDivitt and Ed White were preparing for the world's second spacewalk. Gemini 4's launch went smoothly, and on the third orbit, Ed White left the capsule. Although they didn't know it, the greater sophistication of the Gemini craft made this spacewalk much simpler than Alexei Leonov's just 2 months earlier.
Okay, I'm out.
It was easy to depressurize the entire capsule, so no airlock was needed, and Ed White's spacesuit was fed through an umbilical connected to the spacecraft. Leonov carried his own oxygen in a backpack that made re-entry to the Voskhod capsule that much harder. Within the structure of the Gemini suit was a mesh that prevented the ballooning problem experienced during the Russian spacewalk.
I'm just like $1 million.
The first American spacewalk went so well that NASA assumed working in space presented few obstacles. White's joyride in space gave no indication of the difficulties that lay ahead. The Gemini program had a number of goals, and in December 1965, Gemini 6A and Gemini 7 achieved 2 of them: rendezvous and long-duration flight. The crew of Gemini 7 remained in orbit for 14 days. Mission planners knew that staying in a spacesuit for 2 weeks would be a challenge, so a new version of the G3C spacesuit, called the G5C, was worn by the Gemini 7 astronauts. It replaced the pressure helmet with a zippered hood, and Frank Borman and Jim Lovell became the first people to remove their spacesuits in flight. New technologies were being pioneered in the Gemini spacecraft, and problems with the new systems often meant Gemini flights were only partially successful. The capsule had to be capable of far more complex maneuvers than its predecessor, and longer duration missions required fuel cell technology for electric power. In March 1966, Gemini 8 had successfully rendezvoused and then docked with a target vehicle. But a thruster problem sent the linked craft into a spin. The mission was immediately terminated. The scheduled spacewalk did not take place, and the craft landed in the Pacific, half a world away from the planned landing area. 3 months later, Gemini 9 could not dock because its target vehicle's fairing had not been jettisoned. The scheduled spacewalk went disastrously wrong. When Gene Cernan inflated his suit, it did not want to bend. Exhaustion and a fogging space helmet saw Cernan called back inside. He was overheating. Training for a spacewalk was limited to brief periods of weightlessness in an aircraft, or being suspended in a special jig that moved via an air suspension system across a smooth floor. Neither provided anything like the real thing. Engineers had realized that the current generation of spacesuit worked well sitting in a spacecraft, but when doing strenuous work, its air cooling system was inadequate. New designs were already in train. The next 2 Gemini flights both failed to demonstrate that an astronaut in a spacesuit could do meaningful work in space. Before the final Gemini flight, a new training simulation was tried. A mock-up of the Gemini craft docked to an Agena target vehicle was built in the McDonough School indoor pool. An approximation of the true weightless environment, it allowed astronaut Buzz Aldrin to train for extended periods. Handholds were fitted to the outside of the spacecraft, and the extravehicular work assignments on Gemini 12 were a complete success. It gave NASA planners the confidence to move to the Apollo program and the final stages in America's progress to its moon landing. By 1966, it was apparent that Apollo was well behind schedule. The first manned flight of the program had been delayed by almost a year because of developmental problems with the Apollo spacecraft. NASA was rushing to meet the 1969 moon landing deadline set by President Kennedy, and privately some in the astronaut corps felt that the hurry was not good for the development of a new capsule. NASA had flagged changes to later models of the spacecraft, but the early Block 1 version would still carry a crew in the first manned mission to test systems in Earth orbit. A new spacesuit was being developed for use on the later moon missions, but it would not be ready for Apollo 1, whose astronauts, Gus Grissom, Ed White, and Roger Chaffee, would wear a slightly different version of the Gemini GC-4 suit. All American spacecraft had been pressurized with pure oxygen. This had weight-saving benefits, and by exclusion of nitrogen found in natural air, the danger of bubbles forming in the bloodstream during rapid decompression was eliminated. Though the pure oxygen environment presented a fire danger, nobody had thought to check the real risks. In January 1967, less than a month before the scheduled launch date, the Apollo 1 crew were in their capsule under simulated launch conditions, with the craft being tested under its own power. A spark triggered a fire, and in seconds the crew were dead. The inquiry into the fire found the astronauts had died of asphyxiation from carbon monoxide. Both the spacesuits and the cabin made extensive use of combustible materials. For the program to continue, everything would have to be redesigned. Research into the problems associated with a spacesuit that could be used on the moon had been going on since 1962. The new suit had to be rugged. Designers were still not sure what the lunar surface would present. All previous suits had been fed with oxygen and power from an external source. The moon suit had to be self-contained, and the backpack supplying life support presented problems. The backpack's dimensions and weight were determined by extensive testing, and designers of the life support, battery and communication systems worked within strict parameters. After the Apollo 1 tragedy, flammable components had been removed, and an outer layer of beta cloth, of woven silica fiber coated with Teflon, was added. Many different ways of simulating the moon's 1/6 gravity were trialed. Finally, the A7L suit emerged. Beneath the outer layer, a tight-fitting suit with elbow, wrist, and knee joints of a bellows-like structure that maintained equal volume when bent, allowed freedom of movement absent in previous suits. Beneath the pressure suit, a light, open-weave layer was networked with fine tubes circulating cooling water. This carried away excess body heat that earlier air-cooled suits had not coped with. The pressure suit and the outer protective layer were joined together, with the inner cooling garment remaining separate. On Earth, the whole suit weighed 35 kilograms, with the backpack a further 60 kilograms. It was the A7L that went to the moon with the first 3 successful Apollo lunar missions, and it performed flawlessly. It continued to evolve as subsequent missions became more demanding. The moon suit was robust, and Apollo astronauts had complete confidence in it. No lunar mission ever had a problem with the spacesuit.
We have made it to the start.
With the arrival of the space shuttle, NASA was expecting to do serious work in orbit, and it needed a new spacesuit. The Extravehicular Mobility Unit, or EMU, is a direct descendant of the Apollo A7L. Its main difference is the rigid upper torso. Because they are used in a weightless environment, the new suits could be heavier than the Apollo suit, which operated in lunar gravity. The EMU is not custom-tailored for each user. Components are made in a range of sizes and are interchangeable. Parts are intended to have a useful life of around 15 years. With the shuttle, NASA envisioned servicing satellites in low Earth orbit, but first it had to learn how to do simple tasks. New technologies were combined with the spacesuit. In 1984, astronaut Bruce McCandless, using the Manned Maneuvering Unit, flew independently beside the Space Shuttle Challenger. After 4 hours, he returned safely. The MMU was used for satellite recovery on 2 subsequent occasions, with mixed results. After the Challenger disaster, NASA reviewed all aspects of safety, and the MMU was retired as too risky. A simpler technique emerged. With foot restraints on the shuttle's robotic arm, astronauts could be moved accurately to a site and have a stable work platform. In 1990, the Hubble Space Telescope was launched. Unlike other satellites, Hubble was designed to be visited by the Space Shuttle for regular maintenance and upgrades. Over a 16-year span, there were 5 servicing missions to the telescope, the first being to fix an error in its manufacture.
Is a game-ending activity.
Each servicing mission called for long and complex spacewalks. The EVAs were all thoroughly rehearsed in NASA's neutral buoyancy laboratory. The astronauts are weighted so that they neither rise nor sink, and all the large components that they handle are similarly neutral. Astronauts still have the perception of up and down in neutral buoyancy, unlike in weightlessness. In 1998, work commenced on the International Space Station, a collaboration between the US, Russia, Europe, Japan, and Canada. This was the type of project for which the Space Shuttle had been designed, and the expertise that NASA's astronaut corps had gained was to be put to use for on-orbit construction. As the space station grew, the EMU spacesuit was refined. Increased battery capacity was added so that small heaters in the gloves could keep astronauts' fingers warm during passages through the Earth's shadow. A new safety system was added to the EMU suits. Called SAFER, the Simplified Maneuvering System is designed for emergencies in the rare event that a spacewalker becomes untethered from the space station. It was first tested in 1994, but it has never been used for an actual emergency. With the completion of the ISS in 2011, the Space Shuttle was retired. This meant sole access to the orbiting laboratory was via the Russian Soyuz spacecraft. Cosmonauts and astronauts wear the Russian Sokol flight suit during trips to and from orbit. For maintenance and repair sorties outside the ISS, crew will wear either the EMU or the Russian Orlan spacesuit. Many of the Europeans on board have training in the use of both. The Orlan spacesuit is very practical, designed to be serviced on the space station. It has a rigid torso, with the helmet and visor joined to the suit, and access is via a rear hatch. Cosmonauts wear a water-cooled undergarment similar to the American suit. Unlike the American suit, the Orlan can be put on in just 5 minutes. In the MKS, the latest version of the Orlan, a cosmonaut can safely remain outside for 7 hours. And finally, NASA is working on a new generation suit to meet its future needs. Called the PXS for Prototype Exploration Suit, it also features a rear entry hatch. The PXS has a more advanced life support system and is lighter. A different version, called the Z2, is being developed for use on the surface of Mars. It allows a greater range of movement, and its life support system will take less time to recharge, although neither suit has yet been used in conjunction with its life support backpack.